There is a massive gap between designing a system on paper and watching actual users try to navigate it. When strict engineering assumptions collide head-on with the chaotic reality of software development, the blueprint rarely survives. This chart looks at software projects in the early 1990s. The data shows an incredible failure rate. Only 9 to 16% of projects finished on time and on budget. Everything else overran, overspent, or failed completely. Those failures were largely the product of a single methodology, the Waterfall model. Waterfall is like a physical production line. Analysts lock in requirements up front, pass documents to designers, and hand blueprints to developers. It forces a strict single pass. As verification states, once you start building, you cannot revisit requirements, regardless of what you discover. This breaks down because of a basic human limitation, known as the "I'll know it when I see it" law. People simply cannot read a 200-page technical document and accurately imagine how the final interactive system will feel. They need to touch a functional piece of software before they can articulate what they actually need. Those early projects didn't collapse because the developers couldn't code. They collapsed because the management framework assumed the client had perfect, omniscient foresight. We can see exactly why this single-pass approach fails by looking at physical architecture. Take this installation. The plumbers executed their job exactly to the specification provided. The hardware is securely mounted, and the plumbing works. But because no one tested the holistic user experience during the build process, the final product is functionally useless. In software, you can build every feature perfectly to spec and still end up with a system no one can use. Here is another example of flawless initial execution degrading over time. A batch of pencils stamped with "too cool to do drugs." As the user sharpens the product, the message becomes "cool to do drugs," and eventually just "do drugs." In a strict waterfall environment, you only discover these systemic flaws at the very end of the line. By that point, the cost of going back and integrating new requirements to fix the problem has grown exponentially. A sustainable software architecture has to abandon the fantasy of predicting what the user wants. Instead, it must be built entirely around reacting to their feedback. The waterfall model was formalized in a 1970 paper by Winston Royce, largely for managing massive government contracts. Yet Royce himself explicitly warned that building complex systems in a single pass was a mistake. He wrote that his model was often misinterpreted and advised that developers would need at least a second pass at the requirements to succeed. That ignored advice eventually evolved into what we call incremental and iterative development. Rather than attempting to build the entire system at once, you cut the project into micro-iterations. You capture requirements, design, code, and test over and over in small chunks. Agile methods take this structure and accelerate it, tightening the design, code, test loop so that it happens as frequently as once a day. Shifting requirements are no longer treated as project-ending anomalies. They become expected mathematical inputs. We can see this dynamic play out in a real data processing project, where researchers built a tool to detect latent dehumanization evolving across internet comment sections. The team started with an unstructured raw data source, a stream of dialogue pulled directly from a YouTube video. Their initial requirement was straightforward. They needed to deploy systemic functional linguistics and sentiment analysis to parse the text and map the conversation. This is the output from their first sprint. A vast, complex web showing every analyzed conversation node branching outward from the source. Under a traditional methodology, delivering this visualization would mark the end of the development phase. The requirements were met. But this is precisely when the "I'll know it when I see it" law activates. The moment the user finally sees the data laid out, their initial requirements immediately become obsolete. They utter the most expensive phrase in software engineering: "Wouldn't it be cool if?" Looking at the map, they realized it'd be useful to click a node and change its classification on the fly. In a rigid pipeline, this is massive scope creep. Grafting an interactive tool onto a static visualization would halt the project. But an iterative process easily absorbs the request. The team simply spins up a new iteration, designs the update node interface, and integrates it directly into the map. The best ideas only surface after the initial prototype is built. You have to design your systems specifically to capture those secondary inspirations. Agile provides the philosophy of adaptability, but to execute it without descending into chaos, you need a strict management framework. Scrum is the primary method used to organize and manage these continuous cycles. The process starts with outline planning to establish objectives and baseline architecture. Shifting requirements aren't forced into the active build, they're stored in the product backlog. Finally, the closure phase wraps the project, logging documentation and assessing lessons learned. Scrum works by decoupling the erratic flow of human ideas from the highly structured process of writing code. Coding happens in sprint cycles, fixed blocks of time dedicated to delivering functional increments. Each begins with evaluation, measuring the previous cycle's output. Then, in the selection phase, the team extracts a manageable chunk of work from the backlog to execute. To keep the momentum going, the role of Scrum Master rotates, ensuring continuous leadership and documentation without creating a permanent bottleneck. Unstable requirements no longer threaten the project timeline, and because customers constantly see functional software being delivered on time, trust begins to compound. Masterful software engineering does not require predicting the future perfectly. It requires building an engine capable of continually converting reality into code. Agile provides the philosophy of adaptability, but to execute it without descending into chaos, you need a strict management framework. Scrum is the primary method used to organize and manage these continuous cycles. The process begins with an outline planning phase to design the software architecture. As requirements shift, new ideas aren't forced into the current build, they are stored in a product backlog. Finally, the closure phase wraps up the project and assesses lessons learned. Scrum works by decoupling the erratic flow of human ideas from the highly structured process of writing code. Coding happens in sprint cycles, fixed blocks of time dedicated to delivering functional increments. Each sprint starts with an evaluation phase to measure the previous cycle's output. Then, in the selection phase, the team extracts a manageable chunk of work from the product backlog. To keep the momentum going, the role of Scrum Master rotates, ensuring continuous leadership and documentation without creating a permanent bottleneck. Unstable requirements no longer threaten the project timeline, and because customers constantly see functional software being delivered on time, trust begins to compound. Masterful software engineering does not require predicting the future perfectly. It requires building an engine capable of